Iterators in Python are objects that implement the iterator protocol, consisting of the methods _i, _e, _r, double parenthesis, and _n, _e, double parenthesis. They allow sequential data processing, enabling efficient traversal of collections. This approach supports lazy evaluation, where data is generated on the fly, optimizing memory usage and enhancing performance in large-scale data handling. Iterators are fundamental to Python's data processing, offering a robust abstraction for traversing collections. They enable efficient, memory-conscious programming by employing lazy evaluation patterns, processing elements only as needed. This approach minimizes memory usage, making it ideal for handling large datasets or streams without loading entire collections into memory. An iterator is an object implementing the iterator protocol with _iter, double parenthesis, and _next double parenthesis methods. It maintains an internal state, producing items sequentially. Built-in support exists for lists, tuples, strings, and dictionaries, allowing efficient data traversal without loading entire collections into memory at once. An iterable object, like lists or dictionaries, has an iter die method returning an iterator, allowing multiple iterations without tracking state. In contrast, an iterator object with a _next open parenthesis close parenthesis method maintains its current state, iterating only once. Crucially, all iterators are iterables, but not all iterables are iterators. Python for loops utilize the iterator protocol by calling iter on an iterable to get an iterator. They repeatedly invoke next to access elements, stopping when stop iteration is raised. This efficient, lazy iteration method processes large datasets on demand, minimizing memory usage by generating items as needed. Creating a custom iterator involves defining _iter open parenthesis to return self, and _next open parenthesis to yield the next value or raise stop iteration. Maintain state with instance variables. For example, the odd numbers class iterates over odd numbers up to a limit, demonstrating how to implement and use a custom iterator effectively. The iterator protocol involves 4 key steps. Requesting an iterator by calling _iter, double parenthesis, on an iterable, returning the iterator, fetching items using _next double parenthesis, and signaling completion with stop iteration. This protocol standardizes sequential data access, ensuring seamless integration with Python's iteration constructs, while maintaining simplicity and elegance. Generators simplify the iterator pattern by using function-based syntax with the yield keyword. This allows them to pause and resume execution, producing values on demand. They automatically implement the iterator protocol, reducing boilerplate code and enhancing memory efficiency, making them ideal for handling large datasets or infinite sequences. Generators are special iterators, created with a function using the yield keyword. They pause execution, return a value, and preserve state for future calls, enabling lazy value production. Generators automatically implement _iter, double parenthesis, and _next, double parenthesis methods, reducing boilerplate code and offering memory efficiency by computing values on demand, ideal for large datasets or infinite sequences. Consider a countdown example. A traditional iterator class requires explicit implementation of _iter, double underscore, and _next double underscore methods. In contrast, a generator function simplifies this with the yield keyword, reducing code by 60 to 80%. It efficiently generates values on demand, minimizing memory overhead while maintaining functionality.